Howdy folks, welcome back to Advent of Code 2022. We are going to be looking at day 12 today. Unfortunately, I didn't get part 2 of day 11, but maybe we'll come back to it if we finish the rest of these. So, day 12. Why not search for the chief historian, need the gardener, and the massive farm? Yes, we must go to the massive farm. Okay, you're about to settle near a range of garden plots, and some elves ask if you lend a hand. They'd like to set up fences around each region of plot, so they can't figure out how much fence they need to order, how much it will cost. They hand you a map of the garden plots. Each garden plot goes only a single type of plant is indicated by a single letter on your map. So here's our map. Multiple garden plots are growing in the same region or touching, they form a region. Same type of plant, yeah. Okay, so here's like a region for A, B, C, D, and E. We can see that C here is not a perfect square at all, or even a rectangle. It's a polygon. In order to accurately calculate the fence around the single area, you need to know the area and perimeter. The area is simply the number of garden plots the region has. Garden plot is a square and has 4 sides. The perimeter is the number of sides the garden plots the region not touching them. So basically, it's just the perimeter of that particular space. To kind of use this as an example, it's that whole perimeter here. So the idea here, we can kind of figure this out. If we need to calculate, if we know each of these spaces, we can figure out what the perimeter is pretty easily by looping through them and just seeing how many neighbors they have that are of their same type. Because if they have 2 neighbors, well, then it's 2 spaces. If they have 3 neighbors, it's going to be 1 space. If they have 1 neighbor, it's going to be 3 spaces, etc., etc. Plants of the same type can appear in multiple separate regions, and regions can even appear in said other regions. For example, 5 regions, 1 contain all the O gardens. So this is kind of interesting in that case. All of these O plants are all part of the same region, and then there's this X. Now, the price of fence required is multiplying that region's area by its perimeter, the total price of fencing. Here's the thing that's kind of interesting to me. This X and this O should have the same fence, right? So maybe that's part 2, figuring that out. I guess we can just... Yeah, okay, so they're not worrying about that right now. So it's just, yeah, okay, so it's the area by perimeter, which is a weird way to handle fencing. Yeah. But that's, I guess, just how it's set up. Okay, well, let's take a look. Let's start off with, here's our example. Good. So let's start with this example. All right, so I already have sample map. I've already copied the code over to just pull in a simple map and split by new line, split by this. We're not actually turning these into parsing to integers because they're not integers. They're actually just these things. So what we end up needing to do here is we end up needing to do a flood fill. Because we need to find, let's say I get this R, I need to find all the R's, which is like all of these, right? And you know what, actually I could probably just do this. There we go. And the R's here need to be, like, we want to find all of these to get the area, and also to figure out the perimeter of these, I need to know which ones are all part of this unit. So, and that's kind of important, because otherwise you could just loop through each one, figure out its perimeter and such like that. So, in order to figure this out, we use a flood fill, which is basically we start from any point here and recurse in all 4 directions. Sometimes you could do diagonal too, but I don't think this will work with diagonal. You go in all 4 directions, and just as long as you continue to find these particular things, you keep going. There's 2 caveats here. One, you need to do something to prevent infinite loops, because otherwise you'll just recurse in a circle. And 2, we need to make sure that we've noted that we've processed these so that, like, if I loop through here and I hit here, I don't try to process it all over again. All right, so let's take a look at how we would go about that. All right, so let's get started. Yeah, no, I don't want that. Thank you. So we're going to loop over. Let's get let y equals 0. Oops. Y less than map.length. Y plus plus. Let x equals 0. So basically just loop over everything. Map y dot length, and then plus. So that's not what I want. We want to also note which cells we've already processed, okay? Processed equals, and we're just going to use a map for that. Key equals, oops, x, y, if processed, key, continue. So we don't want to process things twice, right? That would be bad. Yeah, and at the end of it, we do want to mark it as, well, actually, you know what? I'm not going to even do this as process because I want to do this as part of the recursion, okay? Get area, and then we're going to have x and y, okay? So let's see, what do we want to do with this? I mean, that top piece is not a terrible idea there, except that should be greater than, yeah, greater than equal to. This should actually return empty. So what I want to do with this area is I actually want to return a list of coordinates that are part of that area. So if we're off the map, then we don't deal with that. This is definitely not what I want. They're assuming that you're adding up the area. So I do want neighbors equals, and then we're going to do -1y. We've actually done this a couple times already. Let's see if that looks right. Okay, 4 neighbors. And actually my neighbor, that's still not what I want to do. This is, okay, so then I want to say, check chords equals, get area and x and y. But we only want to do that if it is equal to us. So what we're going to say is, if it equals map of y, x, then, or actually if it does not equal, then we continue. So the idea here then is we check if it's a valid coordinate, we loop through all our neighbors. If our neighbor is not the same as us, then give up. Otherwise, we loop into it, okay? So let's see, all, and this is actually going to have our own y and x on it. So that way, chords.push. Can I do that? Does that work? That'd be cool if that works. I didn't realize if that was even possible. Anyway, return all. Oops. And what we want to do also then is we want to process this. We want to add ourselves. But we want to process, so here's the trick. We actually need to process ourselves before we recurse. Because if we process after, well, then the recursion is going to run over its parent, and its parent hasn't actually been processed yet. So as soon as we hit here, processed, grab our key here. No, it's fine. Process key equals true. Okay. And now, so we're going to say if this or neighbor key and x. Whoa, that's not what I wanted to do. X and y or processed neighbor key. So if our neighbor's already been processed, then we're not going to process it again because it's presumably part of the same area that we've handled. Okay, so there's our recursive function. You can see the recursive function is doing a lot of work. Area equals get area x, y, so log area, and that's break. And let's just do this once. All right, let's see how that works. Jeez. Okay. Cannot read properties of undefined reading 3. That is here. Oh, that's why. Because of this. So we actually need to do this check here as well, just to make sure we don't go off the edge of the world. NX, because otherwise we won't actually be able to hook into the map. There we go. Continue. which really means that we probably don't need this check at all, but it doesn't really hurt to keep it there. Okay, so here's our first one. 0, 0, 0, 1, 0, 2, 0, 3. Now you notice it doesn't come back here. Instead it goes 1, 3, 1, 2, 1, 1, 1, 0. Also not picking up any of these. Okay, now it jumps back over to 2, 2. And then 2, 3, 2, 4. And then here. So that looks right. That looks actually pretty good. So that gives us one of those. Let's get a whole list of areas. We'll just post that in there. Push area. Turn off the break. Okay. And then for each of these 4 areas. So what we got to do is we got to loop. So the area is just the length of this. We've got to get the parameter now. So for const chord of area. So for each coordinate pair, let's see, we got to figure out how many neighbors they have. Count. And that is honestly going to be the same thing all over again. We could build the neighbor count into the recursion, but I'm not going to worry about that because I'm not too, unlike the last problem that we did, I'm not too concerned about the runtime of this taking hours. But if you were worried about like this being a lot, having to run over this again, you could always handle it that way. So I want something kind of almost, and the fact that I'm copying this much code is also annoying. So let's see, if map does not equal, I don't care if we processed it at this point. If map equals it, then neighbor count plus plus. All right, so this would actually be coordinate, just so we have that. Okay, so then our neighbor count, if our neighbor count is 1, then it means that we, actually, you know what? Yeah, the perimeter is just going to be, so our neighbor count is how many of our neighbors match us. So if our neighbor count is 1, it means we need 3 fences. If our neighbor count is 0, it means we need 4. If our neighbor count is 4, it means we need 0. So essentially, const perimeter equals 4 minus neighbor count. And let's get our whole total perimeter. Okay, so now equals area.length times total perimeter. Okay, console log. Sure, let's just log that. That's great. Total cost equals 0. And cool, and then we'll console log cost. All right, let's see what we get. Oh boy. Right, because this is supposed to be. No, that's fine. Why is that failing here now? That's 37 that's failing. Right here, okay. So we know this actually should probably be first, because we need to know that ny is valid before checking this, and that actually goes for all of these because they're all doing that same check. We know that y is a valid piece before we bother to check that thing. I mean, we could also have done just of 0 there, but that's fine. Okay. Total cost is 2,053. Let's just see if that works. No. Okay. Then what I want is I also want the I'm gonna get the actual type here. Area. So let's just pull this in. Let's call map y x, so I get the type and the area. Area data type area equals area data. And let's see what that gives us. Okay. Oh, the type area type right, so they're put in there. Eh. Okay. Okay, so type R is 12 and parameter is 19. That's 18. They're getting 18. Hmm. Hmm. Okay. Okay. So there's 4 there. There's 1, 2, 3. Where is that coming from? I need to actually even double check this. Just get the coordinate pairs. Okay, so let's see. Log my neighbor count. Okay. Okay, so yeah, this is all R. 0, 0 has 2, which makes sense. 1, 0 has 2, which doesn't make sense. This should have 1. Why does my neighbor count 2? Checking in X and Y, and then map in X and Y. Okay. Okay, so this one's checking. This one checks 3. Right, and that makes sense. So 1, 1, and for some reason, that neighbor count is not 3. Why not? Map Y. Oh, because I did that backwards. Shouldn't actually really matter, but, well, no. What am I kidding? It totally matters. All right. Oh, that's a V. 0, 2 is a V. Oh, we're going down. Reading that totally wrong. Right, because X and Y. Okay, that's fine then. This one is, okay, 0, 0, 0, 1. Ah, no, that's the fuck up. Oh, no, because this is backwards. Is it? No, it shouldn't be, because 0, 2 shouldn't be a thing that we're checking. Why are we checking 0, 2? Huh. This has something to do with the get area. Uh-huh. Uh-huh. Because I put this backwards. That is probably why. Which means that all the coordinates would be backwards. 1930. 1930. Okay, cool. Well, there you go. Yeah, that's why. So the map was just flipped, but when it was actually putting in the coordinates, which obviously does not work very well. Does that get rid of all of these? Yes, it does. Okay, so let's check out our input. It's a significantly larger map. Hopefully this shouldn't take too long, though. Hopefully I didn't do anything that would cause 140 by 140, cause infinite loops. All right, let's see. Let me run that. Okay, that didn't actually take that long at all. 1437300. Let's give it a shot. Okay, cool. Before we take a look at part 2, let's look at our algorithm. First we get the map. We have our recursive function. The recursive function first, which might not be necessary, but just verifies it's valid. Gets all the neighbors, makes sure that we are processed so that we don't recurse over an infinite loop over the same thing. Adds ourself to the coordinate list because we are an item. Goes through all our neighbors and says, okay, if is our neighbor valid? If the neighbor's not on the map, don't continue. If the neighbor is not the same plant type as us, or it's already been processed, skip it. If it is the same type as us, hasn't been processed, and is on the map, recurse over it. Then when we get those coordinates back from the neighbor, push those all into our coordinates and return. That's the nature of the recursive function. This one doesn't actually have a base case per se. I mean, I guess one of the base cases we go off the map, but the other base case is just we don't have any neighbors that are valid. And that's kind of a more subtle base case to find here because we're not actually explicitly saying that, but it's just if these continue blocks fire for everything, then we just never, which they should eventually. Like that's the kind of the assumption we're making this algorithm is eventually everything that can be processed will be processed and will be done. Then in here, loop over everything in the map, get the key. If it's been processed, finish it. And that means that basically if we get the first element of a block and recurse over it, we'll never process it again in this loop. But we still need to go over it just in case there's something hiding inside one of those. Right? Get the area. Actually push the type of it. This is just for debug purposes. We don't really need it, but get the area there. For here, loop over our area, get the coordinates, again, get the neighbors. Very similar idea. Get our count of neighbors, get the perimeter, sum up our perimeters for all of those neighbors, and then get the total perimeter for all of the coordinates, and that's our cost. Let's take a look at part 2. All right, the L's qualify for a bulk discount. So if using the perimeter, you need to use the number of sides each region has. Each straight section of the fence counts the side regardless of how long it is. The region containing type implants is 4 sides. Right, okay. So basically now the idea is what is the shape of our parallelogram? Now, the fun way that we can handle this is to figure out how many sides we have, we just log, probably with a set, the unique x and y coordinates of everything. So like basically, of every parameter, that is. So basically, if we hit this top here, well, that's a y coordinate that we log. This y coordinate we also log. This one we also log. And for A, we log all 4 of these, but because we're doing a set, they're all going to be the same. And so we only log 1. So that's kind of how I go about that. And that shouldn't be too much work with our current model, I think. Pop that in there. All right, so let's take a look at what we got to do here. Sample there. So this is going to be fine. Get area is going to be fine. I don't actually need to change anything on this when I'm getting my perimeter. I do want to find where the neighbors are, but I also want to find, now I don't actually care about the neighbor count. I'll find not that because I'm looking at the side. So I'm saying, okay, if this is not that, then we got to figure which part is not that. Is it the x that's not or the y that's not? If nx not equal to x, if n, oops, because they're not going to be both be. If ny not equal to y. And in this particular case, for both of these, we log these coordinates because this is going to be a unique side that we need to take care of. So let's take here we're going to say side set, and in here I'm going to add x and x. And I use x and y here as little prepend things because otherwise we could get the same x and y coordinate, and those technically count as different sides, but we need to treat them, and like we need to treat them that way. If we just save the number, it wouldn't work. So now we're not actually going to calculate the perimeter anymore. Here, total perimeter. This is actually going to be the side set dot size, because side set dot size is the number of, it's basically the number of unique steps on x and y that we didn't have a neighbor. And I think, oops, that's part 1. That will work. 863. Oh no, it didn't work. Okay. Regions largest number 4 and S12 the updated prices. So let's see what we get then. Total perimeter side set dot size. Something went wrong about this. All right, 8. So we only got a perimeter of 8. Checking. And let's just check that. Okay. So we only care about the ones where they're not the same now. 4, 0. You know what? Maybe I should actually log that up more appropriately. Let's actually just log this in the case that it was not the same. And x, x, y. So 3, 0. Okay, had 1. Oh, you know why? Because it's not counting the ones that are off the friggin' map. That's why. This counts, oh no, it should actually count them because we hit one here and that should hit there. So let's see. Well, maybe I should just check actually which I have with this. What my side sets are. That might actually be more helpful because then we can see which one is missing and specifically maybe find out why it's missing. All right. Okay, so we've got x4. Okay. Which is this one. Okay. That's great. That's that side one. Y2, which is this one. X1, which is this one. Okay. You know what? Actually, I'm just going to mark these off. We got, what do we got? We got X4, right? Which is this one there. We have Y2, which is actually this one, isn't it? This one. We've got X1, which is this one. We've got Y3, which is I think this one. Oh yeah, Y2 was actually this one. Or this one. So this whole fence there. Okay, so now let's just fill this whole thing in with that. Okay, and then we've got X5, which is 0, 1, 2, 3, 4. How would we get 5 then? Oh, X, which is this one. This fence here. And then Y1, which is actually this one here. And then we've got X3, which is 0, 1, 2. Okay, so that's this one. Again. The hell one's that? Oh, that's this fence, like going the opposite direction. And then Y4, which is 0, 1, 2, 3. Yeah, this one. Okay. How did that show up twice? I think what I might be missing here is corners, maybe? No, it doesn't make sense. That's not how that works. But we are, I think, missing this one. So that's 4, 0, 1, 2. So that's either Y2 or it's probably an X. So 0, 1, 2, 3, 4, 4, X4. No, we did have X4. I just had it wrong because I assumed it was this one. That's actually X3, isn't it? Which we also have. So, oh, but X3 is going to be this one. Yeah, so X4 we have. We're missing this one, which would be X1. Oh, no, there it is. I think I might need to do this again. Kind of got a little messed up. Because this one, like, there's actually 3 sides on it, right? So that's... Oopsie. Okay. No, I actually want to undo all that. Because I imagine... I feel like there's a way to visualize this better, but I don't fully know what it is. So let's just check through this code again. Okay. We go through our neighbors. Okay, so let's just check that maybe and see what we get. If it does not equal that, okay. If it does not equal x. Is this right, though? If the neighbor x does not equal the x, then it's on the side. If the neighbor y does not equal the y, then it's on the top or bottom. That should be fine. Okay. So, okay, that's that. Let's get this done. Because we don't actually have a neighbor count at this point. Okay, so these 3 happen and they don't get anything. Which is kind of inaccurate in a way, again, because of that top, but it doesn't really matter because I don't think we ever have something that spans the entire top. Checking. Okay, so we're checking 3, 0. This is 3, 0. So this is this one. We get IR. Perfect. So that tells us that we add what to the map? Log. Let's get our side set right there. Bunch of debug. Okay, so we add x4 because that's the neighbor. And that is this one. So that's correct. Okay, so that works fine. I'm just going to put this down here and then just kind of riff on that. So these are all processed. They do dot, 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 and this one turns into a fence. Okay. But like this way. Okay, cool. So now we do 3, 0, which is this one, I think. Wait, 3, 0. Oh yeah, 3, 0 down. Okay, so now we go 3, 1. Okay. And 3, 1 apparently 0, 1, 2, 3. This doesn't have any at all. 3, 1, 2. So this is, we have to get to 1, 1 before we get that V. This is wrong. So why doesn't this one get? Oh no, there it is. Checking. Dumb. All right, so this is also an x4. Okay, so that's done. Then we get to 2, 1. That's done. We get to 1, 1. And that actually says, okay, this is going to be a down. I don't know actually how to indicate a down. V. There we go. Little V. And then we get to 0, 1, which does the same thing. Okay. So now we've got two pieces of fence there. We hit 0, 1 done as well. Let's see. 1, 1, 0, 1. Okay, then we hit 2, 2. And that is this one. And that says, okay, well, we've got x1. So that's over here. We get 3, 2. And that one says, okay, this one gives us 3, 3. Which doesn't make a tremendous amount of sense to me. 3, 2, right? 1, 2, 3. Okay, so that's this one. That is this one, and we're on 2. Why is this one connected to anything? We're checking 3, 3. Oh, 3, 3 is here. Oh, that's why. Okay, so this one is actually a down fence there. Okay. Okay, so then we get that. We check. We're checking 4, 2, which is this one, and that one gets a couple of fences. That one gets up, down, and across. So this one actually gets x5, which is this one. I don't know how to indicate these anymore. So we'll just put this down here. This one gets x5, and then it gets, there are better ways of handling this. I just don't know what they are off the top of my head. Y1, which means it's grabbing this one, and then it gets 4, 3. Which goes down and becomes 4, 3 and doesn't get anything to the set. That's the problem right there. This should be adding 3, I think. Oh no, Y3 is already in there. How is Y3 already in there? Oh, because of this. Okay. Cool. And it gives us V. Okay, never mind. So that's fine. All right, 4, 2 done. So now we go to 2, 3. Just an interesting one. Okay, so 0, 1, 2, 3, and that's this one. Okay, so that's this feller, which is going to also have multiple. So this one has, okay, first of all, it says, all right, we're checking the x over here, which is going to be, doesn't know, it adds x3. No, it doesn't add anything for this. Does this add? I don't think this adds anything because it's y1 and x3, both of which we, well, I think it's this one actually, or the y. See, now I'm losing track of this. This is an x, so this is x1. which is already in the thing, but that's basically over. Okay, and so then we have this next one, which is 3, 3. This adds x3 onto the list, which is great because we didn't have x3 before, did we? I feel like then, what the hell? Oh, no, yeah, because that was that. Okay. Then it hits this next one, and it says, okay, now we go and we go down, and we add y4 to the list. So, yeah, okay, we're done. So what are we missing here? What fence are we missing? We've got fence here. This one, this inner corner, is that fenced? That's an interesting question. In particular, each inside and outside the fence not connected across the middle of the region. That's funny. Okay, the number of sides each region has, but that shouldn't matter. Shouldn't matter because it's on the end. Okay, so let's look at this original one. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that does make sense. That's fine. Let's see which one we're missing. We have y1, which we do have. Well, maybe I'll just write these out manually. So we have y1 there. We have x3. That's actually y0, isn't it? You know what? I think that is exactly why these aren't being counted. These two corners, they are not actually being counted because nothing there. If we look here, yeah, if we go this way, we're going to get the x. If we go this way, we're getting the y. But if we go this way, we need to go this way to get that particular y. So that's the issue. All right, so if this goes off the end, we actually need to split this up. And this one, and I'm going to use 0 for this, just so that I don't get into trouble with that. Okay, and the reason I need to split that up is because I need to know whether it was the x or the y that went off the edge of the world. So if it is the x, then we actually side add x and x. Like that. And here we would add the y. And I think that fixes our issue. So let's see. Let's take these out, because I think that will actually fix that particular problem. Oh boy, I don't want the side set. Thank you. Okay, so that gives me 10. That gives me 1002 now, which is still off. So what part is off? 120, 16. Okay, so that C type is off now. C is supposed to have a perimeter of 22 somehow. Okay. C is supposed to have a perimeter of 22. The C... Oh, because there's multiple of... No, there's just one, isn't it? There's a couple. Okay. Okay, so that's why there's multiple groups of C. Well, then let's go in here and let's say, okay, if... let's look at our areas then. Type equals C. Just make sure we're getting that. Area. And let's just see what our areas are. Okay, we have that one. Okay, perfect. And then we have this one. Oh, that's because they're adding them all together and I'm not. So that does confuse that a little bit. Let's do this then. So total cost by type. Total cost of type equals that if. So what I'm doing here is I'm actually just setting it so that, oh boy, that's actually going to be kind of complicated to figure out. Yeah, never mind. I was thinking maybe I could just hash it like that, but I don't want to do that because that'll make things really complex and hard to deal with. Just make sure I didn't break anything there. All right, so C is actually going to be that's interesting. That's interesting because here I took 14 and 16 and 1 and 4. So they want me to add both of these together, I think. That still doesn't quite count to 20. Oh, no, that's interesting. 14 and 22. 14 and... No, even if I added those, I get 15 and 20, which is wrong. Did they use a different... Word of example before? How are you dealing with this? Oh, because... Wait, does that count as... Okay. This is an area of 17, 12 sides. This map. Okay, so B. I'm looking at B. How does this... Okay, so 2 regions full type B trans each with 4 sides. So this is 16 and 16. Be careful when calculating the fence around the region full type A plants, in particular each section. The fence is an inside and outside, so the fence is not connected across the middle of the region. Where the 2 B prints do not touch diagonally. It doesn't... Yeah, I mean, the system that we have would have found that out, I think. Because it's checking all of that. So this is weird. This is really weird. Because, okay, so they have 14 C plants. But here, I get 15 C plants. There are 15. There are 15 of them. So why are they getting 14? Interesting. Interesting. It's because if I run part 1, over the sample, yeah, so I have the C here and the C here. And that came out with the correct number. Interesting. Wonder if there's any other issues like that. Let's try part 2 again. Let's just see. All right. F plants, 10 and 12. Oops. 10 and 9. Okay, so that is also a big problem. Where's our F? F, okay. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's definitely something wrong with the F's. You know what it is. These are 2 distinct sides. That's the problem. That's the problem we're into. These are 2 separate sides, but I'm counting them as 1. Oh, boy. Okay, so that's actually more complex then. This is more complicated because we can't just copy those sides in like that, because that doesn't work for little sticky out bits like that. So what we want to do then, we actually need to traverse around these. Then we need to do like a whole traversal, which is kind of fun in a way. Let's see. So really what we could do is we could find any of this area that are on the outside and do like a left, or kind of like go clockwise around them, which means that if we are here, we go down and down and down until we no longer go down, in which case we go inward, okay, and then out. This one would add 2 to the list. This one would not add any, actually, but then how do we know to get here? Basically need to walk around the whole perimeter. Maybe. So really to do this then we'd actually have to be looking at a grid of 9. So we'd look at our current thing and say, okay, I am here on this grid. I know that I have no neighbor here, so that adds to that. I have no neighbor here, that adds to that. I know that I need to walk to this one, but that, God, there's so many cases for that. So many weird cases. Hmm. But I think that's the only way to do it, because yeah, because what I'm doing right now is not going to work, actually. Getting these sides. It is not going to work at all. I mean, this'll be fine. We can leave these alone, but this is the problem. Hmm. What we could do is we could say whenever this could be interesting. We could do the same list of like whenever we hit one of these, we just also remember. So let's say we're doing the X here. We just remember all the, or no, is this the, yeah, this is the X. We just remember all the Y coordinates also that we hit that on. And then we can actually see if there's any break in those. So that might work. Let's do that then. This is no longer side set. This is going to be an object. And let's make a little function in here. Add side key extra. This needs to be an equals. Okay, so now key equals an array, and then cool. So now we're just going to add side x and then y. Okay. Now we go here. This is going to be of y, and the extra is going to be nx. And this, I believe, is actually going to be the same down here, and the same down here. Okay. So now when we get to the end of this, I want to see what is my side set. No, actually, I don't want to see it at the side set. I want to see it at the end here. Type side set. Okay, so let's run through that. Okay, so here's our R. Okay, so -1. See, these are contiguous, right? Contiguous blocks is fine. Now when we get to the C was fine, actually, that was fine. I don't know what's up with that. So the F was the problem. Okay, so this is contiguous, kind of you know what, those should actually be sets. Actually, shouldn't they? And yeah, just because I don't want the duplicates in there. I'm not totally sure that I even got in there multiple times. All right, so here's that, and this, so this, see, there we go. That is a break. So that's where we would add in another one. And let's see. Is that the only one that F had? Were we off by, how many were off by F? 10. Right. The parameter is undefined, but I think we were off by not, I don't know how many we're off by. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're off by 1. So that would fix the problem with the F. All right, so let's do this then. So let's go over set, and actually I need value of, I think I can do this in an object. Values equals, oh, let's just do this. Value.sort. And now we need to go through breaks equals 0, or, runs equals 1. So we start off with 1 for length, if value.length minus, this is sorted, so I should be able to do this, minus value, oh my god, value of I, value of I minus 1 is greater than 1. Well, does not equal 1, runs plus plus. And so then essentially we have how many runs? Runs. And then here we say total runs plus equals runs, and then this is going to be runs. Total runs. And our perimeter is now total runs. You know what? I kind of want to comment this out for a second just to see if any of this works. Side set is not iterable. Right up from side set. Oh wait, side set's not. You know what? That's probably because I can't do that with an object. So that's fine. Sure. This is a good idea, just so that we don't destroy the original array. I don't know if it matters here, but that's fine. Oh, that's interesting because now that is 21. Oh, but then there's the additional parameter there. F is now 11. Okay, so 10, 4, 22, 12. So these are still off by 2. Huh. Okay. Where would, oh, this is also one that would be something that I would want to look at because that's another jump, that Y jump. So let's see what we had for F on that. RICF. Okay. So what jump is that? What is this? This is 9. Okay, so this is gonna be 8. X8. X8 only has 1 in it. That's that Y. It doesn't get this last one, which is kind of interesting. Let's do this. If Y equals 4, just because I know that that is the Y that I'm looking at. Okay. I'm looking for R, I'm looking for C, I'm looking for F. Okay. So this is going to be, which one is this? This is going to be 8, 4. So that's this one. We check, we check, we check. And neither of these are actually, yeah, those are both. So it's the C that I'm interested in here. This C, 7, 4. Uh-huh. Oh, but that would have given us offensive X7. Oh, so here's that one. Oh, so that totally should have been a break then. That's a 0 and that's the 4. So that was a break. What am I getting here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's actually 2 breaks in here. So that's where we get the 11. Interesting. Okay, so we dealt with that one. We dealt with this one. So now we've got, okay, 1, 2, 3, 4, 5, 6, 7. We know we're fixing this one. 8, 9, 10, 11, 12. So we're still missing one of these. We've got this one handled. This is the, okay, so we got Y -1. That's this one. We've got this one handled, which is going to be what? X9? X10. Yeah, okay, so X10, that's that. Then we come up here. This is going to be Y4. We have that one. We actually have 2 of those, right? So this is going to be X9. Okay, we get that. This is going to be Y5. We have that one. This is going to be another, what is this, X7? Another X7, right, which is that one. Okay, and this is going to be that other Y4. Okay, we get that. This is going to be X6, which has 2. This one pointing down here will be Y1, I believe. Okay, that has 2. This is going to be X something. What is this? X9. Yep, and then this one is coming up Y2, which is missing. That one's missing. Interesting. Okay, so let's go back here and let's save Y equals 1. Okay, so let's see, where is my F? Okay, so if Y equals 1, okay, so that is this one. That is checking, it should be, right, this is one, no, this one is missing, right? So this is, All right, so this is actually y equals 0. Okay, because I need the, yeah, I need the piece of the actual plot that I'm looking at. Okay, so y equals 0. We're checking two things. We're checking 7, 0 and 7, 1. So this is the one. Oh, that's 8. That's interesting. So that, right, this is y, this is x8. So this should actually be a y on this. Because the x's are the same. The y's are what's different. I mean, that shouldn't really matter too much. It should add that y of 1. Oh, it's right there. Y1, 8, and 7. Why are we reading 8 and 7? That's a little odd. Oh, because it's coming out from these 2 points. It's coming out from each. Okay, so we did the... Now we've got the concave because they're technically hitting the same one. Okay, so what we're going to do is we're going to actually put in x, our own x to here. Because it should technically be the same across the whole list. So that is, I don't think I need to do it for there. I could do it anyway. And remember, these are just string keys, so I can do whatever I want here, really, and it should be fine. And now let's look at our f. And now we have our y 0 to 1. Perfect. And that has 12. Okay. Fun stuff. Let's see if that fixes anything at all. What am I console logging here? This one. Okay, so now I get 1206, and I think, yep, that is what they want. Very nice. Very nice. I'm going to take this out, and then we'll run this over our input. Whew, that was a wild one. You can see those edge cases really become problematic. 857,941, or 940. Let's see what we get here. That's not the right answer. Too high. Uh-oh. Too high. Too high, too high, too high. That's not ideal. There's probably a lot of areas in here. Yeah. Yeah, there's a lot of these. And that is too high. So we got it correct with this. And so what that tells me is there's probably something. Because, see, that we got that little concave issue. And then the convex issue here. That should handle no matter how large it is, right? So it's... So I wonder what else in here. I need to make this smaller. Okay. Okay. Okay, so this one, this BBB. Gosh. That's not going to be very pleasant to try to figure out, is it? Well, let's see what we can do. Okay, so it took me entirely too long to figure this out, after which I literally tested every single reasonable case that this could happen. I realized sort. Sort does not sort numerically. Sorts alphabetically. So we end up with wonderful things. Like normally in the sort, we're expecting that this will always be bigger than this. But it's not. Because this is wrong. And so then we get negatives. And in the case of a negative, that's not equal to 1. Even if it's negative 1. Yeah. See, this, and also the sorting is completely off in this case. 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There should not be a gap here. So I think this is how you appropriately sort. Let's find out. Yeah. So that, I think, is going to fix that issue. So that was the issue, and that was why, is we were just getting too many runs. All right, so let's see. What do we get now? 849332. That, I think, is smaller. Yeah, it is smaller. There we go. Okay. I will tell you, that took me a long time to figure out and debug through. It's fun stuff. Okay, so what are we doing here? Get area doesn't actually change. We'll just go over our code briefly. Get area doesn't change. Total cost does. We're now looking at our sides. So when we get our neighbors, before the main course, we look at our sides. When we get our neighbors, we now are saying, okay, if we're off the map or if the neighbor doesn't match, we now tell it, okay, which X were we on and which one were we going to and which Y are we doing. So we're basically building a list of all those little points where we found a neighbor and keying it off of what were we looking at. Then we go through here, we go through all those keys and we say, okay, how many gaps are there? How many individual lengths are there? Add those all together, and then we have our total runs. Whew, that was a long one. Not as long as 11 because 11 just didn't finish, but yeah, that was fun. I actually I did enjoy that. One of the real issues I'm starting to see with this advent of code thing is, let's go back here. They give us an example here, they give us an example here, right? They give us a couple examples here. And in all the examples I have, I never ran into that case because they didn't give us a secondary example that was big enough. Like they could have given us an example that, well, maybe this is just me. Maybe it's just because of the code I'm writing. But in this case, the reason we ran into that was because we had something across the barrier that was across 10 elements, and no example that they give us is that big. It'd be really nice if they just gave us like an example, right? That was just bloody massive, or not bloody massive, but like something that's like 20 by 20 across, right? Not 140 by 140, but something that's big that we know what it should be. That way, I can actually check my code on something that's a little bit easier for me to check because, yeah, you can see all the tests I wrote here just to try various combinations, but I was trying small. I never thought to try big until I actually looked at this and thought, well, maybe let me look at these runs. So there you go. I hope that was interesting. It was certainly fun for me. I'll see y'all next time.